Okay, so now let's move on to the next topic. Actually, I have started this clip earlier, but then I got interrupted. So I got interrupted along the way. So I'm just gonna use whatever I have here. I'm not gonna rewrite it again. So basically, the topics that we have to talk about are two more. There are two more things that we have to talk about. So the first thing is the householders method, and the second one is the QR method. So these two methods can be used to have to be used together in order to find the eigenvalues. The second requirement is that these two methods can only work for a symmetric matrix. So if your metric is not symmetric, you cannot use them. Okay. I think something is wrong here. Whatever. So for the symmetric matrix, then let's see, for example, if you have a matrix that looks like this, you can have any number along the diagonal line. It doesn't matter. Any number is fine. But if this is 10, then the position, if the position is of the row 1, column 2 is 10, the position in the row 2, column 1 has to be 10. If the position 3, 1, 3, 1 is 5, 1, 3 is 5, then position 3, 1 has to also be 5. So it has to be, symmetric along the diagonal line. So this is the definition of a symmetric matrix. Okay, so the way that it works is that you have to have, a symmetric matrix as an input, and then you input into the householders method. Actually, householder is the name of a person. So what the householder is going to do is that it is going to change the symmetric matrix to be a tridiagonal matrix. So what does it mean to be a tridiagonal matrix? It's going to be a matrix that has the non-zero values, that is allowed to have non-zero value on the diagonal line and also on the upper and lower diagonal line. So these are going to be the lines that allow non-zero values. For other positions, you need to have 0. Okay, so the householder is basically going to change the symmetric matrix to be in the form of the tridiagonal matrix. And once you have a tridiagonal matrix, then your QR method is going to find the eigenvalues of the matrix. The nice thing about the QR method is that it can find all eigenvalues. Okay, so this is pretty much it about the householder and the QR underlying idea. So let's just begin with the householder. As mentioned in the previous clip, for the householder, I'm going to go into details of the theory behind the householder method. So bear with me, it's going to be a little bit difficult. So for the householder method, first let me give you the definition. And this definition is called householder transformation matrix. Okay, so for the householder transformation matrix, let's assume there is a vector W equals to, W1 up to Wn, or we can say that W is a member of the Rn, This is the symbol that say W is a real number with n dimension. And we also assume W transpose W equals to 1. This is the dot product of the W. If this is true, then the matrix P equals to I minus 2 times W. W transpose is called the Houesholder transformation matrix. Or I can put a box around this matrix because I'm going to have to use it a lot later on. The property of P, properties of P. First of all, P has to be symmetric, right? P needs to be symmetric. And the second is that P has a property that's called orthogonal. And when the matrix is orthogonal, it means that P equals to P inverse equals to P transpose. So this is so cool for the P that, you know, P is the same as the P inverse, is the same as the P transpose. If you have a matrix with this property, that means that that matrix is called an orthogonal matrix. So we're going to use this property a lot when we prove the Houesholder method. Okay, so the goal is that GOAL, we want to multiply this P with the matrix A to transform A to be tridiagonal. Okay, let's just see in the picture. So, and we do it column by column. So column by column and row by row and row by row. So the first iteration, we're going to do it the first column and the first row. In the second iteration, we're going to do in the second column and the second row, and so on and so forth. So let's just see the illustration of it. So if you multiply P, this is the first iteration, or the first time that we run the code. So in the first iteration, we multiply whatever P that you created with the A in the first iteration. And then you also multiply the same P at the back. So basically, what you do is that you're going to multiply P here with the A. So this is A. And then with the P here. So A is A11, A12, A13 up until A1N. A21, A22 up until A2N. Hey, sorry. My bad. A21, A31, A31 up until AN1. Everything up until ANN. Okay, so if you have, this multiplication, what the Houesholder method is suggesting is that you're going to multiply this P, with this first column of A. So this first column of A is going to be multiplied with the P1, right? And what we want is that we want to have, after the multiplication, we want the numbers in the green box to be equal to 0. If my number in the green box is 0, then that means in the first column, I have the form of the tridiagonal form, right? So this is okay. So what we're going to do is that we're going to keep doing it and then make this first column to be 0. And then in the second row, we're going to make this column to be 0. In the third row, we're going to make this column to be 0. So keep doing it. You're going to transform all the columns that you don't need to be 0. And similarly for the P1 in the back, you're going to change this first row to be 0. second row to be 0, third row to be 0, and so on and so forth. So this is the step that we are going to do for the householder method. So let's just prove it in the first column here. So this P1 is going to do with this first column. This P1 is going to do with this first row. So we just see it one side only. So proving it, we just see P1. So if you multiply P1 with the first column of A1, 1, A2, 1, A3, 1 up until AN1. So let me expand the P. So the P is, the way that we construct the P is that in the first column and the first row, it's going to be just 1 and the remaining values are 0. And this is because we want to multiply this P with the A1, 1, A2, 1 up until AN1. If you multiply this first column of A with the P, then eventually you're gonna get just A1, 1 in the first row, which is okay, right? Because we don't want to touch this A1, 1. It's okay, A1, 1 can be anything. We don't need to change it. What we care is this, these numbers starting from the third row. These numbers have to be 0. So we'll just construct the P in such a way that, you know, in the first column and the first row, we don't really touch anything. Here in the letter column and the letter rows, we'll just call it P hat. So P hat is gonna have the size of n minus 1 times n minus 1. All right, so this P hat is going to be multiplied by this A2, 1 up until AN1. We call this vector y hat. So if you, after the multiplication, basically the first number in the resulting multiplication is going to be A1, 1. And then the later on, these are going to be P hat times y hat, right? So P hat times y hat, the size of this vector is just going to be n minus 1 times 1, right? So let us expand this P hat y hat in just a minute. So eventually you're gonna have A1, 1 and then P hat y hat. Let me just make it longer. Okay. So the multiplication of P hat y hat, the end result, you just want A1, 1, any number alpha, and then the remaining have to be 0. So basically you want P hat y hat to be equal to alpha and then 0, 0, 0, 0. Alpha can be the resulting value after P hat times y hat, right? We don't know yet. So let's just see that if we want P hat y hat, then we expand it a little bit. This P, remember, is the householder transformation matrix. So this is a householder transformation matrix. It's a metric with the size reduced by 1. So this is I n minus 1 times n minus 1 minus 2 w hat transpose. So w hat is just w starting from row number 2 up until row number n. So you want this multiplication to be multiplied with y hat. So the thing in the parenthesis is the P hat multiplied with y hat. And so if you move y into the parenthesis, I times y hat is just y hat minus 2 w hat transpose y hat. This one is just a scalar because it's a dot product of the two vectors. So let me just call it assume equals to r, any number r. So you have y hat minus 2w hat r. This is going to be equals to, you know, this one. Alpha 0, 0, 0, 0. So you want it to be equal to alpha and then 0. So if you expand this, y hat minus 2w hat r. Y hat is just basically a21 minus 2w2r, a31 minus 2w3r, a41 minus 2w4r, and so on. an1 minus 2wnr. This is equals to alpha 0, 0, 0, 0, 0. So if you just do it one by one, that means that a21 minus 2w2r is equal to alpha. And a31 minus 2w3r is equal to 0. a41 minus 2w4r is equal to 0. an1 minus 2wnr nr is also equal to 0. So let me just see here. So here from the equation in the box, just move the side a little bit. You have 2w2r equals to a21 minus alpha. And then from these equations, they're pretty much the same, just change the index. So just 2wjr equals to aj1, and this is for j equals from 3, 4, 5 up until n. I'm just gonna call this equation number 1 and this equation number 2. Okay, let me just pause a little bit. Can I pause it? Okay, let's come back. So if we have equation number 1 and equation number 2, then if we square both sides of equation 1 and 2. Actually, for equation number 2, you have a lot of equation, right? You have 2w3r equals to a31, 2w4r equals to a41, and so on. So you have n minus 2 equations. So we're just gonna square both sides and then of all the equations that we have, and then add them up. So for equation number 1, you have 4w2 square r square plus the left-hand side of equation number 2 is just 4w3 square r square plus 4w4 square r square plus 4w5 square r square plus until plus 4wn square r square, and this is equal to a21 minus alpha, everything square, plus a31 square plus a41 square plus up until an1 square. I'm going to write in terms of the summation. So it's 4r square times summation j equals from 2 to n wj, because I already put the index as a j square, and the right hand side, this is a21 minus alpha square plus summation aj1 square j from 3 to n. You expand things in the parentheses here, so this is a21 square minus 2a21 alpha plus alpha square plus the summation j from 3 to n aj1 square. So you can include a21 into the summation. So this is 4r square sum j from 2 to n wj square. So this is 4r square summation j from 2 to n wj square equals to summation j from 2 to n aj1 square minus 2a21 alpha plus alpha square. We're gonna have to take care of this first summation first. From this first summation, we know that from previously, let me just make this, call this equation number 3. So from previously, we know that W transpose W equals to 1. So this is summation j equals from 1 to n w j square equals to 1 because it's a dot product of each w, right? If we assume w1 equals to 0, hence we have summation j from 2 to n wj square equals to 1. So you know that, this summation is just this summation. So this summation is just 1. So from 3, we have 4r square equals to summation j from 2 to n a j1 square minus 2a21 alpha plus alpha square. So let's take care of this j and alpha. I'm just going to call this equation number 4. Okay, so previously, again, you know that, p hat, y hat equals to alpha 0, 0, 0, 0, 0. So if you square both sides, and in order to square both sides of a vector, it's going to be something like this. So it's p hat y hat transpose times p hat y hat. And this is going to be equal to alpha 0, 0, 0, 0, 0 times alpha 0, 0, 0, 0. So you have to concern about the direction too. So on the right hand side, I'm just going to switch it to the left hand side, which is going to be only alpha square. And the left-hand side, if you expand the transpose, this is going to be y hat transpose p hat, oops, y hat transpose p hat transpose p hat and y hat. P hat transpose p hat. This is actually equals to identity matrix since p hat is orthogonal. So when a metric is orthogonal, p hat equals to p hat inverse, right? So if you have p, and also equals to p hat transpose. So if you have p hat equals to p hat inverse, then p transpose p, this is just going to be the identity metric, so you can just cut it out. So basically you're going to have alpha square equals to y hat transpose y hat. And you know that your y is just a21, a31 up until an1 times a21, a31 up until an1. You multiply these two vectors together, you have alpha square equal to summation j from 2 to n a j1 square. So basically you have alpha square is just the same as the summation of this. So from 4, we have 4r square equals to summation j from 2 to n a j1 square minus 2 alpha a to 1, and then plus alpha square, which is also the summation 1 to n a j1 square. You add these two things together, you have 4r square equals to 2 sum j from 1 to n a j1 square minus 2 alpha a to 1, divide everything by 2, so I have 2r square is summation j from 1 to n a j1 square minus alpha a to 1. So having this equation, this is equation number 5, I guess. Okay. So from equation number 5, we select alpha to be, I'll just write it down, the minus of the psi of a to 1 times summation j from 2 to n, a j1 square, everything is to the 1/2. So if you select alpha to be this value, psi means just the psi of a to 1. So let's say if a to 1 is 100, then the psi of 100 is plus 1. If A21 is minus 100, then the sign of minus 100 is just minus 1. So you just use either a plus or a minus for the sign of the A21. By choosing this, okay, if alpha is as selected above, equation number 5 will be something like this. So it's going to be 2r squared equal to summation j from 2 to n aj1 squared minus absolute value of a21 summation j from 1 to n aj1 squared to the 1/2. If you plug in the selected alpha and your equation number 5 is like that, this can guarantee GUARA guarantee that R will not be 0 as long as all AJ1 is not 0. So, selected, you can select any other choice of the alpha too, but if you select alpha this way, then you can guarantee that you can also find the R that's non-zero. So we'll just do it this way. So if you don't really understand anything, starting from the beginning of the proof until the end of the proof, it's pretty much quite okay. But if you can try to understand it. But from now on are the things that you have to understand, okay? So in conclusion, to do householder method. You have to do it. The number of iterations is n minus 2, right? You have to do it n minus 2 times. And the reason is that if you have a metric A that looks like that, and you want tridiagonal matrix, so it's going to be something like that. For the tridiagonal matrix, so the first iteration, you do it in the first column, second, do it in the second column. So you just do it up until the n minus 2 columns. So you just have to change n minus 2 columns and also n minus 2 row at the same time. N minus 2 columns to be 0. So you have to do it n minus 2 times. Let's just see in each round, you have to calculate the following. Let's see for the first round, round 1. The first round is that step 1, calculate all parameters. The first parameter that you have to do is alpha. Alpha is, we define it to be the minus of the sign A21, A21 times summation j from 2 to n aj1 squared, everything goes to the 1/2. So basically, if you have a matrix A, then you can easily calculate your alpha, right? Because you just use the value in the matrix A, basically. Once you have the alpha, then your R is going to be 1/2 alpha square minus 1/2 A21 alpha, everything to the 1/2. And this R is calculated from, actually from equation number 5 by just plugging in this to be equal to alpha square, and then you solve for the r. So this is r. So you know alpha here. You can use alpha in calculating the r, and you can just plug in A21 here. So r is also pretty easily to calculate. After you have alpha, you have r, then your W1 is 0 for the first round. W2 is actually going to be A21 minus alpha divided by 2r. So this is from equation number 5, and this is from equation, I believe, number 1. So let me just go back to equation number 1. So here, equation number 1 here, if you move 2r to be the denominator, then your W2 is just A21 minus alpha divided by 2r. So this is what we have. So this is W2. Wj is just going to be AJ1 divided by 2r. This is from equation number 3, and actually this is for j equals to 3, 4, 5 up until n. So basically these w's are just w in the vector w. Okay, so you just plug in all the w into a vector form. So this is step 2. Put all the w into the vector form. And step 3, what we just need to do is calculate the Houesholder transformation formation matrix. So the Houesholder transformation matrix P is just I minus 2W W transpose. And once you have the Houesholder transformation matrix, then step number 4, your new A is just going to be P. So this is P in the first round times your original A, the A given by the problem, and then this is just the P. So you update your A, and then you use your A to calculate alpha, R, W, and P second round in the second round. And once you have, A in the third round, you use the A in the third round to find the P in the third round, and so on and so forth. So in the kth round, R-O-U-N-D, use the following formulas. So first, alpha equal to minus sine of a k plus 1k, and then summation j equals to k from k equal from k plus 1 to n, a j k square, everything to the 1/2. R is 1/2 alpha square minus 1/2 alpha a k plus 1k to the 1/2. W1 up until WKs are all 0, but then starting from k plus 1, this is going to be AK plus 1k minus alpha divided by 2r, and WJ equal to AJK 2r, J starting from k plus 2, k plus 3 up until n. So these are going to be the formula that you use. Once you have all the W, of course, you can find the P, right? So PK is just I minus 2W in the kth round, and W kth round transpose and then k, a in the k plus 1 round is just pk times ak times pk. Okay, so this is pretty much it for the theory behind the householders method. Let's see, for example, before we go into the MATLAB. So A is just 4, 1 minus 2 and 2, 1, 2, 0, 1 minus 2, 0, 3 minus 2, 2, 1 minus 2 minus 1. So when k is the first round, in the first round we find alpha, so this is minus the sine of a to 1 times summation j from 2 to n, aj1 square, everything to the half. So sine of a to 1 is 1, so this is the positive number, so it's just the, plus 1 here. The summation from row number 2 to n, so this is 1 square plus minus 2 square plus 2 square, into the 1/2, so this like everything in this column will be the square and then add them together. So basically we have everything is going to be minus 3 for the alpha, so r is just a half alpha square minus a half a to 1 alpha, everything to the 1/2, so you have 1/2 minus 3 square minus 1/2, a to 1 is 1, alpha is minus 3, everything to the 1/2, and you get square root of 6. W1 is 0, W2 is just a to 1 minus alpha divided by 2r. 1 minus alpha is minus 3 divided by 2 times square root of 6. So you have 2 divided by square root of 6. W3 is A31 divided by 2r, so A31 is minus 2 divided by 2 times square root of 6, and this is minus 1 divided by 6, the square root of 6. W4 is A41 divided by 2r, and A41 is 2 divided by 2 square root of 6, and this is 1 over square root of 6. So your W is basically 0, and then 2 over root 6 minus 1 over root 6 and 1 over square root of 6. Okay, so this is your W. So my P1 is just I minus 2W, W transpose. So I is just, an identity matrix with the 4x4 size. Okay, so this is I minus 2 times W, which is 0, 2 over root 6 minus 1 divided by root 6 and 1 divided by square root of 6 times 0, 2 over square root of 6 minus 1 over square root of 6. And finally, it's 1 over square root of 6. Okay. Note though that if you multiply these two vectors together, it's not a dot product, it's going to give you a big matrix. The reason why I say big is a 4x4, right? So it's not like a dot product that you get a scalar, it's going to be, a matrix. So you do the calculation. Eventually you're gonna have 1, 0, 0, 0, 0, 0, 0, and this is minus 1/3, 2/3, minus 2/3, 2/3, 2/3, 1/3, minus 2/3, 1/3, and 2/3. So after the calculation, this is what you get for the matrix P. Note though again that this metric is symmetric, right? Symmetric and orthogonal. So once you have the matrix P, you calculate A in the second round. So it's going to be P in this round times A and then times P in this round. So basically this is gonna be, after you do the calculation, right, it's gonna be 4 minus 3, 0, 0, and this is minus 3, 0, 0, 10 third, 1 4 third, 1 5 third, minus 4 third, 4 third, minus 4 third, and minus 1. So it's, as you can see, that we successfully transformed the first row and the first column to be in the form of tridiagonal. What we only need to do is we need to change, 4 third to be 0, and we're going to be done. So in round number two, this is when k is equal to 2. K is the number of round, actually. So for k is 2, alpha is minus sine of a 3, 2, and then summation j from 3 to 4, n is 4, right? A j 2 square, everything to the 1/2. So, A32 in this case, it's just 1 here. This is A32. So A row 3 column 2 is 1. The sign is just the positive. So this is just, plus 1 here. And the summation starting from row J. So this summation is going to sum over these two numbers square. So it's going to be 1 square plus 4 third square, everything to the 1/2, and I get minus 5 divided by 3. So my R is just a half alpha square. Hang on, let me just find the paper here. A half alpha square minus a half alpha A32, everything to the 1/2. So I have 1/2 alpha square is minus 5 thirds square minus 1/2 minus 5 third. A32 is just 1. Everything to the 1/2. A32 is just 1, right? So what I have is 2 square root of 5 divided by 3. And then my W is just going to be, the first two values is 0. W3 is actually going to be A32 minus alpha divided by 2R, which is 1 minus alpha, which is minus 5 third divided by 2 times R, which is 2 square root of 5 divided by 3, whatever I have 2 square root of 5, if I'm not wrong. And the last W4 is just A42 divided by 2R. So A42 is square root of, A42 is just 4 third. So this is 4 third. Oops. 4 third divided by 2 times R, which is 2 root 5 over 3. So what I have is I only have root 5 over 5. And then once I have my W, I can use my W to find P2, which is going to be I minus 2 W transpose. Once I have my P2, I can find my A3 to be, P2 times A2 times P2. And, after doing the calculation, this is 4 minus 3, 0, 0, minus 3, 0, 0, 10 third, minus 5 third, minus 5 third, 0, 0, minus 33 divided by 25, 68 over 75, 68 over 75, 149 over 75. So as you can see that now I have achieved my tridiagonal form. So let's just move on to MATLAB. So now the theory is pretty much done. So I'm gonna go to MATLAB in the next clip. All right. Okay.